Okay, a very good evening to one and all. Welcome to the second live stream by Einstein Academy. So today we will wrap up what we haven't finished covering for atomic structure, and then we will move on to the new chapter on chemical bonding. Good evening to one and all. Welcome to the second. As always, you are free to type in any comments in under the comment section, and I'll be more than happy to answer any queries that you might have on the content or for the matter of the live stream. Okay, so let's do a brief recap of what we have covered last lesson in the chapter of atomic structure. So let's start with the first learning outcome. Identify and describe protons, neutrons, and electrons in terms of their relative charges and relative masses. So to that, the answer would be this simply. The proton has a charge of +1, and the electron has a charge of -1, and the charge of a neutron is 0. Where the relative masses of the protons and neutrons is 1 unit is to 1 unit, whereas the mass of the electron, you don't really have to remember this number. We can just say that the mass of the electron is very much negligible as compared to the mass of the proton and the neutron. Okay, so that sums up the answer to learning outcome A. Now, learning outcome B, deduce the behavior of beams of protons, neutrons, and electrons in an electric field. So the main thing is that positive charges are always deflected towards the negative plate, whereas negative charges are deflected towards the positive plate, and moreover, the angle of deflection is actually proportional to the charge over mass ratio. The higher the charge of the particle, the greater the angle of deflection, and the larger the mass of the particle, the smaller the angle of deflection. For the neutron, since it's electrically neutral, it's neither attracted towards the negative plate nor the positive plate, and hence it will pass straight through an electric field without being deflected at all. So that's the answer to the learning outcome B. Learning outcome C, describe the distribution of mass and charges within an atom. So the protons and neutrons are situated in the nucleus of the atom, and hence the majority of the mass is distributed only within the center of the atom, whereas for the charges, in the nucleus is positively charged. That's where the protons reside, whereas the electrons revolve around the atom, and the negative charges are just revolving around the atom. So that's the answer to learning outcome C. Deduce the number of protons, neutrons, and electrons present in both atoms and ions given proton and nucleon number. So to that, this is kind of the answer. Okay, so you have the chemical symbol as well as the mass number, which is the bigger number, and the mass number is defined as the sum of the number of protons and neutrons in a nucleus, whereas the atomic number is simply also called the proton number, which is just the number of protons in the nucleus. If you were to take the number of nucleons, the nucleon number, subtract away the proton number, that will give you the number of neutrons that's given in the atom or the ion. Okay, so that basically sums up learning outcome D and E part 1. So for E part 2, distinguish between isotopes on the basis of different numbers of neutrons present. So as mentioned, the definition for isotopes is that they are atoms of the same element with the same number of protons but different number of neutrons. So this is a definition that you need to remember, since it's explicitly written in the learning outcomes that you have to distinguish between isotopes on the basis of different number of neutrons present. And just to emphasize that since isotopes have the same number of protons, they also have the same number of electrons, and hence the chemical properties of isotopes is exactly the same, whereas the physical properties will slightly differ due to the fact of the difference in masses. Okay, then we moved on to talk about atomic orbitals, and this is the first key part in JCH2 chemistry that is very new to the students out there. And the idea is that every atom has a number of electrons, and you need to place the electrons in the correct orbitals based on their energy levels. So we also talk about how can we find out the different energy levels of the different atomic orbitals, and to that, in order to get this answer, and this answer is actually embedded in the periodic table, and I actually went through with you all how to get these energy levels. So to the periodic table here. So like this again is level 1, and this part is the S block, and this part is the P block, whereas this part is the D block. So the lowest energy level orbital is level 1. So I'll put here 1, 2, 3, 4. So level 1 s. So right at the bottom is 1s orbital, and then the next one you move on like 2s followed by 2p. So 2s is the next higher energy orbital, and then you have 2p. So just to like to remind you that the shape of the s orbital is that of the sphere. And the shape of the p orbital is in a dumbbell shape along either the px orbital, the pz orbital, or the py orbital, and the p orbitals actually come in a set of 3. There's no way to have only one p orbital on its own only. If you have a p orbital, it always comes as a set of 3 orbitals. Whereas this is the shape of the d orbitals, is the shape of 2 dumbbell shape. It can be along the xy along in between the xy axis, and that will be the dxy orbital. If it's in between the x and the z axis, it will be the dxz orbital. And if it's in between the yz orbital, it will be called the dyz orbital. If it's along the x and y axis directly, it will be called the dx square minus y square orbital. Whereas this special one with a dumbbell shape along the z axis with a donut shape in between, that's called the dz square orbital. Again, the d orbitals come in a set of 5, and there's no way to just have only one d orbital. So back to this, right? The periodic table, the lowest energy orbital 1s. Okay, wait, so probably let me just erase this for a moment. Okay, the lowest energy orbital is 1s, and there's only one set of s orbital. For the 2s orbital, there's only one set of s orbital because it's a sphere. And then the next highest set is the 2p orbital, and there will be 3 sets of p orbitals, px, py, and pz. Then after that, you move on to the next one, which is this level 3, level 3s, then level 3p. So level 3s, there will again be one set of orbitals which can hold 2 electrons. So I emphasize again that each orbital can hold exactly 2 electrons, and they must be in the opposite spin based on the Pauli exclusion principle. The next highest energy orbital is that of the 3p. Again, it comes as a set of 3, the 3px, 3py, 3pz, and then after, when you hit the 3p, it will now be the 4s, and then the 3d. So the next is 4s, one of the spheres, and then when you reach 3d, it's the set of 5 orbitals. And then after that, after 3d, it will be 4p, and then so on and so forth. When you fill in the number of electrons, let's say there's 10 electrons to fill in, you go to the lowest energy orbital and you fill in 1. And just remember that the next electron that goes into the same orbital, it has to be the opposite spin based on the Pauli exclusion principle. Then we fill in the next highest energy orbital, 1, 2, again opposite spin. And then now if you want to fill in the next electron, it will go in like that. And then the next electron that go in, we have an option. We can either put the electron here with the same spin as the previous one, or we can put the electron in the same orbital with the opposite spin. Hund's rule says that you should always place the electrons singly occupied in the orbital before you pair them up. This is because that if you put the electrons in the same orbital, it will actually experience greater inter-electronic repulsion. Since electrons are all negatively charged, they will actually repel each other. And if you actually place the orbitals of opposite spins in the same orbital, it will actually lead to greater repulsion and hence greater destabilization of the atom. So the next electron will go in like that, again like singly occupied with the same spin. The next one will go in here, and then the next one here. So based on this, we will have filled in 10 electrons. If the 11 one were to go in, this will be the 11, this will be the 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so I'd just like to mention that the electronic configuration where there's 24 electrons, right, which is basically the atom of chromium, is actually not like that. And what you actually do is that you actually place this electron and you promote this electron from the 4s orbital up the 3d. So the idea is that half-filled d orbitals are particularly stable. To be honest, this is not really the true reason, because if you actually study the the atoms in the lower block, you will realize that half-filled d orbitals is not really particularly stable, and this is not really the real reason. But for the purpose of A level, we can just say that half-filled d orbitals and fully filled d orbitals are particularly stable. So when you reach a configuration where you have this situation, where you can have the option of either like that, 2 electrons in the 4s orbital and 4 in the 3d, what the atom will do, what the atom will prefer to do is to promote an electron from the 4s orbital and move it up to the 3d orbital, creating a half-filled d orbital, a system of half-filled d orbitals which is particularly stable. Then if we were to fill in the next electron, it would then go back down to here, and then the next one here, the next one here, the next one here, the next one here. Again, when you reach this system, the atom would again prefer to promote the electron up from the 4s orbital up to the 3d orbital, creating a system of creating a system of fully filled d orbital. Again, the reasoning being that somehow a fully filled d orbital is particularly stable. So for the electronic configuration of chromium and copper, this anomaly happens. So let me write that out in a while. Okay, and then like if you have one more electron to fill in, you will fill in like that. Okay, so again I emphasize, you fill in the number of electrons from the lowest energy level up, and when electrons, you have a choice to pair electrons up or to put them in separate orbitals with the same spin. You will always prefer to put the electrons in separate orbitals of the same spin first. Okay, so let me again like talk about this electronic configuration of chromium and copper in particular. So let me insert a blank slide. So 24 electrons and 29 electrons respectively. Okay, so we have chromium with 24 electrons. Okay, so like the first level is the 1s orbital, and we'll put 2 electrons in the 1s orbital. Then we will next put 2 electrons in the 2s orbital, 6 electrons in the 2p orbital. Then the next will be 3s2, 3p6, 4. Okay, so this is the situation that's supposed to be. So if you count the number of electrons, right, 2 plus 2 is 4, 4 plus 6 is 10, plus 2 is 12, 18, 20, and 24. So this is a possible electronic configuration for chromium, which has 24 electrons. However, this is not the correct answer, because like for chromium, again, there's an anomaly. So the correct electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. I would choose to promote the electron from one of the electrons in the 4s orbital to the 3d orbital, like that, hence creating a system whereby I have a set of half-filled d orbitals. So this is the correct electronic configuration of chromium with 24 electrons. On the other hand, if I have copper with 29 electrons, so I'm going, instead of having 1s, okay, so if you do not consider this anomaly, this will be the electronic configuration: 3s2, 3p6, 4s2, and then 3d9. Okay, however, this is not the correct answer, because we can actually choose again to promote one of the electrons from the 4s orbital to the 3d orbital, hence creating a set of fully filled d orbitals. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Okay, and this is the correct answer, because again the official answer that's given is that it creates a set of fully filled 3d orbitals which is particularly stable. Okay, I hope this makes sense to y'all. If y'all are not, y'all can type your questions in the comment section, and I'll be more than happy to answer them. Okay, I hope this Okay, so to this learning outcome, describe the number and relative energies of the s, p, and d orbitals for the principal quantum numbers 1, 2, and 3. So again, the 1, 2, 3 is basically the level. So like this is the this first number here is the principal quantum number. So like I've covered 1, 2, and 3, and including the 4s. After the 3d will be the 4p. So all the way until the 4s and the 4p. Describe the shapes of the s, p, and d orbitals. So again, the s is a sphere. The p looks like a dumbbell shape. So s is a sphere. The p will look like a dumbbell shape like this, and it's along the 3 different possible directions, x, y, and z direction. For the d orbitals, there's 2 different types. One is like that, whereby you have, it's like a butterfly shape. Sorry for the bad drawing. Oops. Like this, and they can be along the x, in between the x and y axis, in between the x and z axis, in between the y and z axis, or along directly the x and y axis. And then you have another type of orbital, which is a dumbbell. Only one of this exists with a dumbbell shape in between. So you kind of like have to practice drawing this a bit, so that in the exam you'll be able to reproduce the drawing of these orbitals. So and do you need to know how to draw it? Absolutely, because like if you look at the learning outcome, it says that you have to describe the shape. Basically just draw it. Okay, and state the electronic configuration of atoms and ions given the proton number and charge. So basically the steps to doing this is to first figure out the total number of electrons that the atoms and ions have, and then you just fill it up based on this energy level diagram of the different orbitals. Okay, so that was where we left off for the last streaming, and I hope that this recap helps you all revise for these learning outcomes. So we'll now move on to the next part of the content. Okay, so ionization energy is defined as the amount of energy required to remove 1 electron from each atom or ion in a mole of gaseous atoms ions, producing 1 mole of gaseous cations. So yeah, so the removal of the first electron from the atom is the first ionization energy, and if you subsequently remove more electrons, it will be called the second and third ionization energy, so on and so forth. The second ionization energy involves the removal of the second electron, and then so on and so forth. So let me like summarize this in the form of an equation. So in the first equation, we have a sodium gaseous atom. So notice that in the definition, especially when we study energetics, we will come back to this. The definition is that is the amount of energy required to remove 1 electron in a mole of gaseous. The word here is gaseous, so it's particularly important. When we come to the chapter of energetics, you will realize that the state symbols are particularly important, because that is the actual definition of the different terms of the energy when we study energetics. More on that when we study energetics. But in this equation, it's terribly important that it's from Na gas to Na plus gas. Like this Na liquid to Na liquid plus electron. This equation does not represent the first ionization energy of the sodium atom. Okay, so the first ionization energy removes 1 electron from the sodium gaseous atom, forming 1 mole of gaseous sodium cation. And notice that the first ionization energy is actually positively charged. Why do we okay, so we haven't learned energetics yet, but if you recall from your secondary school chemistry, right? If it's positive charge, it means that the reaction is actually endothermic, if you recall this, which means that energy must energy enters into the system. So basically what it means is that you need to use energy to bombard against the sodium atom so that you can actually remove the electron from the sodium atom. And the reason that you need energy to do so is because the valence electron of the sodium atom is actually negatively charged and attracted towards the nucleus of the sodium atom. Hence, since it's attracted, in order to pull the thing out, you actually need to use energy to pull it apart. And that's the reason why it's positively charged. You need to input energy into the system so that you can overcome the attraction between the sodium nucleus and the valence electron so that you can break it apart. So if we were to go back to like the old way of describing electronic structure, right? Like for example, this is the sodium atom. Right in the middle is the nucleus. Like you have 2 electrons here, and then 8 electrons. And then in the third shell, wait, let me see. It's sodium in, yeah, sodium is in like here. Yeah, in the third shell, this is the valence electron, and this valence electron is actually positively attracted towards the nucleus, and hence you have to use energy, input energy into the system so that you can overcome this attraction to pull out this electron from this atom. This electron would actually be this electron here. Okay, so the first ionization energy of magnesium to pull out the first electron from a gaseous magnesium atom to form 1 mole of gaseous magnesium 1 plus charge cation, and again is a positive charge. The second ionization energy is to remove the second electron from now the magnesium 1 plus cation to form the magnesium 2 plus gaseous cation. Notice that the successive ionization energies is usually much bigger than the previous ionization energy. So let's try to understand why. For this magnesium atom, the valence electron is attracted to the nucleus. And for this one, the valence electron is also attracted to the nucleus. When the difference between the magnesium gaseous atom and the Mg plus gaseous atom is in the attraction of the nucleus to the next valence electron. Okay, so let me explain further about this. Okay, so let me check for magnesium first. So magnesium, the proton number is 12, meaning that it has 12 protons and 12 electrons to begin with. Okay, so for the magnesium gaseous atom, we have 12 protons and we have 12 electrons, which means that the 12 electrons is attracted to 12 protons, whereas for the Mg plus gaseous ion, because it has already lost 1 electron, it means that the total number of electrons is just 11, but the total number of protons in the nucleus still remains as 12. For this situation, we have 12 electrons attracted by 12 protons, whereas for this situation, we have 11 electrons held on by the same number of protons, and overall, the effect is that the smaller number of electrons will actually, on average, be more attracted to the same number of protons, and hence it will always require more energy to pull the next electron out, because the attraction felt by the remaining electrons is always larger, and hence successive ionization energy is always higher. Okay, so ionization energies are usually positive because energy is required to overcome the electrostatic forces of attraction between the nucleus and the electron to be removed. And moreover, successive ionization energies increase because the remaining number of electrons decreases and are more strongly attracted to the unchanged positive charge of the nucleus. Okay, so like for example, in this example, the remaining number of electrons is more strongly attracted to the unchanged number of protons. 11 guys being put by 12 is a more strong attraction than 12 guys being put by 12 protons in the nucleus. Okay, factors influencing ionization energy. So as we go from atom to atom in the periodic table, we would like to understand what are some of the factors that will help us decide whether the ionization energy of this atom is it larger than the other atom or not. And these three points here are basically the factors that will help us decide which the ionization energy of which atom is actually larger. So these are the 3 points: the size of the positive nuclear charge. So as mentioned, since the valence electron is actually attracted to the nucleus and energy is required to overcome this attraction, if the size of the positive nuclear charge is actually larger, meaning that if the number of protons is actually higher, the valence electron will be more strongly attracted to the nucleus, and hence more energy is required to overcome the attraction and more energy is required to remove this valence electron. So that's factor 1, the size of the positive nuclear charge. As the size of the positive nuclear charge increases, the attraction of the valence electron to the nucleus increases, and hence the ionization energy will increase. Basically, the nucleus will attract the valence electron more strongly. Atomic and ionic radius. So I'm going back to the simpler view that we learned in secondary school, right? So like this is the nucleus and then the valence electron. So like if we compare this case to the second case, whereby it's 3 shells. Okay, so I'm just omitting all the electrons in the inner shell because I'm not interested in that. When we are removing the electrons, we are removing the one in the valence shell. So notice that as the electron is further away from the nucleus, as the atomic and ionic radius increases, right, it will be further away from the nucleus, and it will again be less strongly attracted to the nucleus just because of the fact that the distance between the nucleus to the valence electrons will actually be larger as the atomic and ionic radius increases. Okay, so like this point, as atomic and ionic radius increases, the outermost electron is further away from the nucleus and hence less strongly attracted to the nucleus. And if it's less strongly attracted to the nucleus, less energy will be required to remove this valence electron, and ionization energy will actually go down. Okay, screening effect. Okay, so the idea about screening effect is the following. If you have a nucleus and then what we want to do, right, is we want to remove this electron from the atom. So this valence electron is being attracted to the nucleus, but the thing is that this inner shell electron is kind of like acting like a shoe that shoes the attraction of the nucleus towards this valence electron. So in this situation, we have basically these two electrons are acting as a shoe to shoe the attraction of the nucleus towards this valence electron. And compared to this situation, like let's say we have two shells of electrons and the one that we want to remove is in the third shell, right? So like there's two electrons in the inner shell and then like there's 8 here. So a total of 8 plus 2 electrons is shielding the attraction of the nucleus from this valence electron. So as the shielding effect increases, the number of electrons in the inner shell with respect to this valence electrons increases. This shielding effect will actually go up and it will block more of the attraction of the nucleus towards the valence electron. And if this attraction of the nucleus to the valence electron is blocked, then the attraction will be weaker and the ionization energy will drop because less energy is required to overcome this attraction. Okay, so like what I've said, the outermost electron is shielded from the attraction of the nucleus by the inner electron. So it's terribly important to understand that it's only the inner electrons that shield the outermost electrons. And basically the shielding effect is dependent on the number of only by the number of inner shell electrons. The greater the number of inner shell electrons, the greater the screening effect, and the less strongly the outermost electron will be attracted to the nucleus and less energy will be required to remove it. Okay, so like we have gone through the 3 factors that will determine basically how large the ionization energy of each atom is, and we would like to summarize. So like these 3 factors, right? These 3 factors actually determine how strongly the nucleus attracts the valence electron. Of course, the stronger the attraction, the higher the ionization energy. So we would like to summarize, after we have discussed these 3 things, right? What is the overall effect of these 3 factors on any single particularly atom? And we would like to summarize this based using the term called effective nuclear charge. The term effective nuclear charge is how effective the nucleus is in attracting the valence electron. So it's used to describe the effective attraction between the nucleus and the outermost electron, having taken into consideration of all the 3 factors influencing ionization energies. So of course, the greater the effective nuclear charge, the more effective the nucleus is in attracting the valence electron, the greater will it be the ionization energy, because more energy will be required to overcome the attraction between the nucleus and the valence electron. Okay, so as you can see, right, this is a plot of ionization energy versus the atomic number. So the first ionization energy of hydrogen is here, and then the ionization energy of helium actually goes up. When you go from lithium to beryllium, it actually goes up, and in fact, when you go across the period 2 from lithium all the way to neon, you can see that the general trend is that when you go across the period, the ionization energy actually increases. Okay, you can see that the trend is like upwards. And again, for this class of elements in period 3, there is an upward trend in the ionization energy, which means that ionization energy actually increases across the period. Okay, so now I would like to discuss, based on the 3 factors that we have gone through, why is it that ionization energies actually increase across a period? Okay, so again, when you come across any questions that are testing you on ionization energy, just always discuss the number of protons and the screening effect, and also the atomic radius or ionic radius, and then conclude using the effective nuclear charge before you then say does the ionization energy increase or decrease. So again, if we were to use period 2 as an example, as you go from lithium to neon, you can see this green line. The general trend is that the ionization energy actually goes up across period 2. So in general across a period, so first we talk about the number of protons. The number of protons increases. If you were to not believe me, we can go back to the periodic table. Lithium has 3 protons, beryllium has 4, 5, 6, 7, 8, 9, 10. This should be obvious because the successive element from the previous one always has one more proton. So the number of protons actually increases across a period. Okay, how about the screening effect? The screening effect remains relatively constant as the electrons are added to the same subshell as the outermost electron. Okay, so let me emphasize again. Screening effect only depends on the number of inner shell electrons. Let me draw the electronic configuration for lithium, right? So like you see lithium, it's like 2 and then 1, right? And then let's just say carbon, it's like 1, 2, and then like 1, 2, 3, 4. Which is the valence electron that we're trying to remove in the first ionization energy? It is actually this in lithium and this in carbon. How many inner shell electrons is actually shielding the nucleus from the valence electron in lithium? The answer is 2. Just this 2, right? Because there are only 2 inner shell electrons. How about for the case of carbon? It's also 2. Because the number of inner shell electrons that is shielding the carbon nucleus from this valence electron is again exactly 2. Okay, so the point is that when you go across the period, because the electrons are added to the most outer shell, and the number of inner shell electrons always remain the same, so the shielding effect or the screening effect actually remains constant as you go across the period. Since the number of protons increases and the screening effect remains relatively constant, we can just ignore the screening effect, and the number of protons will mean increasing, will mean that the effective nuclear charge actually increases across a period. Since the effective nuclear charge increases across a period, the attraction between the nucleus and the valence electron increases and the ionization energy will go up. And hence this explains why is it that across the period the general trend is that the ionization energy actually increases. Okay, so consequently the effective nuclear charge in general increases across a period and the ionization energy increases across a period. Okay, so we mentioned that from lithium to neon, the ionization energy generally increases. However, we can see that there's actually 2 anomalies. The boron actually has a lower ionization energy as compared to beryllium. Notice that there's a slight dip here in this graph. And the ionization energy of oxygen is actually lower than that of nitrogen. Again, notice that the ionization energy of oxygen is slightly lower than that of nitrogen. So this is really an anomaly to the overall general trend in the increase in the ionization energy. And we now would like to discuss these 2 anomalies. Okay, so boron has a lower ionization energy than beryllium, even though it has 1 more proton. So let me emphasize again, the key to doing such question, to figuring out this anomaly, right? First of all, at the end of the day, you should really remember that there are actually 2 anomalies, and you should remember the reason for it. So, and you having know the reason, you'll be able to deduce which 2 elements are the one that has this anomaly. So the key to doing this is to first write out the electronic configuration of the atoms that we're interested in. So if you look at beryllium, the electronic configuration here is given as 2s2, and then for boron, right, is 2s2, 2p1. Okay, so when you remove the electrons, you always remove the one that is the highest energy level. So for beryllium, the electron will be removed from the 2s orbital, whereas for boron, you'll be removing the electron from the 2p orbital. So if I were to write from the bottom, right, so like 1s, for beryllium this will be like 1s2, then for 2s2, like this, right? So this is for beryllium, and the electron will be removed, the electron to be removed will be this one. Whereas for the case of boron, this is the 1s orbital and 2 electrons, and then 2s is 2 electrons, but it has 1 more electron which is in the 2p orbital. Okay, and the electron to be removed is in the 2p orbital. So the point here that I want to make is that the electron to be removed from boron is from a 2p orbital, whereas the electron to be removed from beryllium is from a 2s orbital. And the thing about the difference between the 2p and the 2s orbital is that on average, the 2p orbital is actually further away from the nucleus as compared to the 2s orbital. So again, the 2s orbital looks like this, whereas the 2p orbital looks like this. Okay, so for the 2p orbital, the electron is actually further away from the nucleus on average as compared to the 2s orbital. And since it's further away from the nucleus, it will actually, the 2p electron will actually be less strongly attracted to the nucleus. And since it's less strongly attracted, it will actually require less energy to remove as compared to the beryllium. And hence, this explains why the ionization energy of boron is actually lower than that of beryllium. Okay, so summarizing that, the first ionization of energy of boron, the way you answer the question is that the first ionization energy of boron involves the removal of a 2p electron, which is further away from the nucleus and better shielded than the 2s electron of beryllium. So I think it's okay not to say this part, the better shielded, but it's definitely true that it's further away from the nucleus. And since it's further away from the nucleus, it's less strongly attracted to the nucleus and less energy is required to remove it as compared to the 2s electron of beryllium. Hence, boron has a lower ionization energy as compared to beryllium. Okay, so the other anomaly is this. So oxygen. So again, I told you that the way that you should do this, right, is to first write out the electronic configuration of the two atoms that is in discussion. So nitrogen, the electronic configuration is 2s2, 2p3, whereas the electronic configuration of oxygen is 2s2, 2p4. Okay, so I'm going to write out like I'm just going to write the levels, the orbitals and the electrons for the 2s and the 2p orbitals. So this is 2s, there's 2 electrons here. Whereas for the 2p, right, remember for the Hund's rule, this is how we fill up the electrons in the 2p orbital, singly occupied first before placing them in the same orbital, because if you were to place the electron in the same orbital, you will actually experience greater repulsion because the electrons are actually closer to each other on average. Whereas for this oxygen, right, it will be this case, 2s, 2 electrons here. And since it's 2p4, right, I have to put 1 electron, 1, 2, 3, and the fourth one will go in here. Notice that I'm forced to put the electron into the same orbital with the opposite spin. So the electron that I'm going to remove, the first ionization energy of oxygen will involve the removal of this electron. Whereas for the first ionization energy of nitrogen, it will involve the removal of this electron. The difference between this electron and this electron is that this electron is paired. And since this electron is paired, it will actually experience greater repulsion, and the greater repulsion will actually destabilize the electron, resulting in it being more easily removed from the atom. And this electron, on the other hand, is not paired, so it will be more strongly it doesn't have this repulsion. So this electron of nitrogen actually requires more energy to remove as compared to this destabilized electron due to the pairing of the electron in the oxygen. Okay, so oxygen has a lower ionization energy than nitrogen, even though it has one more proton. The first IE of oxygen involves the removal of a 2p electron that is paired. And the paired electron experiences greater repulsion than the unpaired 2p electron of nitrogen, and it's less stable. And since it's less stable, being repelled by the electron, less energy is required to remove it as compared to the unpaired 2p electron of nitrogen. Okay, so that basically sums up the variation of the ionization energy across the period. So again, I emphasize it's like nothing difficult. You just need to understand what are the factors that you need to consider, and the factors that you have to consider is none other than these three. Okay, so the size of the nuclear charge increases across the period. The atomic radius remains relatively quite constant across the period. It actually decreases, but that's another topic for itself. The screening effect remains relatively constant because the electrons are added to the same subshell and the number of inner shell electrons remains the same. Since the size of the positive nuclear charge increases but the screening effect remains relatively constant, the effective nuclear charge increases, and hence more energy is required to remove the valence electron as you go across the different atoms in the same period. Okay, so again, just discuss these three factors, summarized by saying effective nuclear charge, and then therefore, does the ionization energy increase or decrease? Okay, so having discussed across the period, we would now like to discuss what happens down the group. Okay, so even without looking at the answer, let's just, again, it's just using these three factors to discuss. So when you go down the group, right, the size of the positive nuclear charge will increase. So yeah, as you can see, right, if you go from sodium to potassium, the number of protons increases from 11 to 19. How about the atomic and ionic radius? So as you go from, like, say, sodium to potassium, right, there's actually one more electron shell. So if there's one more electron shell, certainly the atomic and ionic radius will increase, and the valence electron will be further away from the nucleus as compared to the element in the higher group. Okay, so basically the atomic radius increases, and the attraction of the valence electron to the nucleus for the element in the lower part of the group will actually be weaker. For the screening effect, it actually increases because as you go down the group, the number of inner shell electrons will actually increase by exactly one full inner shell electrons. So the screening effect actually increases down the group. So again, for this situation, we have a conflicting, we have like a competing factor, because the size of the nuclear charge increases would increase the effective nuclear charge, whereas for the atomic radius, ionic radius increasing, it will actually decrease the nuclear charge because it's now further away from the nucleus, and the screening effect increasing actually decreases the nuclear charge. So we have two factors that decreases the effective nuclear charge, and we have one factor that increases the effective nuclear charge. So the question is, how do we decide which one is actually more important? And the answer is that we can't decide. We have to let nature decide for us. So what you actually do is you actually do an experiment, and you actually measure the first ionization energy of, like, say, sodium and potassium, and you experimentally find out which one of the ionization energy is actually higher. And if you do the experiment, you will find out that when you go down the group, right, the ionization energy actually decreases, which would mean that the factors of atomic radius being larger and the screening effect being larger outweighs the increase in the size of the positive nuclear charge. Okay, and hence effective nuclear charge actually decreases down the group. So that was the experimental part. So how do we actually phrase it in answering a question? So this is kind of the answer. Okay, so when you go down the group, the number of protons increases. However, this is actually outweighed by the increase in screening effect due to the increase in the number of electron shells down the group, and is also outweighed by the increase in atomic radius down the group. So overall, the effective nuclear charge actually decreases down the group, and hence the ionization energy actually decreases down the group. Okay, so basically I'm discussing, like, the factors that will influence the ionization energy across the period and also down the group. Okay, so explain the factors influencing the ionization energy of elements. So, like, these are the three factors. Okay, something that's very important. Regardless of whether you're discussing across the period or down the group, these three are the factors. Having discussed these three factors, summarize by using the term effective nuclear charge before saying whether the ionization energy increase or decrease. Okay, give me a moment. Okay, so as you can see here, right, there's actually no questions under this checkbox. So kind of like there is no A-level questions that's directly asking you just based on this learning outcome. So we'll move on to the next point first, which is still on the topic of ionization energy, before we'll do these questions as practice to apply our concepts. Okay, so like this is the successive ionization energies of sodium. Okay, so still on the topic of ionization energy before. Okay, so basically what this graph is saying is that, right, this is the first ionization energy of sodium, and this is the amount of energy. It seems to be at 0, but I assure you it's not 0. It's like close to 0. Okay, like for this one, the this energy is the process for this Na gas to becoming Na plus gas plus electron. Okay, so this is the amount of energy that's required for this process. Okay, and then like this is the second ionization energy. So this is the energy for this process, Na plus gas to becoming Na2 plus gas plus electron. And then like let me see. Okay, so as another example, so like this 7 one, right, will stand for Na6 plus gas, removing one electron from the Na6 plus cation to form Na7 plus electron. Okay, so basically this is how to read the graph. This is the ionization energy, the value for the first ionization energy, the second ionization energy, third ionization energy, so on and so forth. Okay, so the important thing to get from this graph, right, is always the jumps. Notice that like from the second ionization energy to the ninth ionization energy, right, this is like kind of quite a gentle increase. Whereas for the difference between the first ionization energy and the second ionization energy, right, this jump is actually much bigger than this like milder increase. And again, there's another big jump, right? There's the difference between the ninth ionization energy and the 10th ionization energy is actually very large. So what is it trying to tell us, right? It's trying to tell us that, okay, so again, let me go back to the old picture, right? So like Na, if, okay, sorry, let me just draw in all the electrons first. Okay, so like this is the first ionization energy, the first electron that will be removed. Notice that the second electron to be removed, right, is actually in the inner principal quantum shell as compared to the valence electron. And since it's the inner principal quantum shell, it will actually be more strongly attracted to the nucleus, and hence a larger amount of energy is actually required to remove that electron. And so the point is that whenever there's a large jump, it always signifies that the electron to be removed from the next electron with the higher jump one will always be removed from an inner principal quantum shell. And this will actually allow you to tell the group number of the element, because like if the jump is from 1 to 2, right, it's telling you that the second electron is actually from an inner principal quantum shell. And since the second electron is from the inner principal quantum shell, right, there's exactly only one electron in the valence shell. And since the group number is actually kind of the representative of the number of electrons in the valence shell, right, it will actually tell you that this element is in group 1. How about the third electron that we're going to remove? The third electron that we are going to remove, right, it's actually this electron. Oops. The third electron that we're going to remove is actually this electron, right? But notice that this electron is actually in the same principal quantum shell as the second one, and hence there isn't a very large jump from 2 to 3. So when there's a gentle increase, it means that the successive electrons to be removed is from the same principal quantum shell. Only when there's a large jump, it will mean that the next electron is from the inner principal quantum shell. So notice like this is 1, 2, 3, 4, 5, 6, 7, 8, right? So as we remove 1, 2, 3, 4, 5, 6, 7, 8, right, the 10th electron, which is this one, will now correspond to again the inner principal quantum shell, which is more closely which is closer to the nucleus and more strongly attracted, and hence again a much larger amount of energy is required to this a much larger amount of energy is required to remove this electron. So the main takeaway from this graph is that there are two things you can take away. Whenever there's a jump, it must mean that the electron in that jump must be from an inner principal quantum shell. And there's also one more thing that you can tell. Is notice that like it can tell you that since there's only one electron in the valence shell, this is in the second subshell, and this is in the third subshell. So it also tells you that, right, there is 3 layers of shell. Okay, this is provided that this total number of electrons that's removed, right, this is for all the number of electrons. So obviously if this is only a representative and there's actually, you can actually remove more electrons from the element, right, then it's not possible to conclude how many number of shells there are. However, if the question says that this is basically all the ionization energies of this element, then it's possible to say that, well, we have only one shell here that we can remove, the second shell here that we can remove, and the third shell that we can remove, so it must be in period 3. And since the second electron is in the inner principal quantum shell, there's exactly only one valence electron, and hence is in group 1. Then we'll be able to conclude that this element is from period 3 group 1, and hence it is the sodium atom. So the main types of question that can be associated with this type of ionization energy graphs is that they'll show you the ionization energy graphs and ask you to decide the identity of the atom. Okay, so this summarizes what I've mentioned just now. There are relatively bigger jumps between the first and second ionization energies, as well as between the 9th and 10th ionization energy. Between the first and the second, and between the 9th and the 10th. The second ionization energy involves the removal of an inner 2p electron that is more strongly attracted to the nucleus than the outermost 3s electron, whereas the 10th ionization energy here involves the removal of an innermost 1s electron that is more strongly attracted to the nucleus than the previous outer 2s electron. Okay, so as mentioned just now, there are 3 different sets of energy levels. There are 3 shells in the atom, so like 3 sets of shell, 1, 2, and 3. And since that, so the atom belongs to group 1, so period 3 group 1, sodium atom. Okay, so deduce the electronic configurations of elements from successive ionization energy data. So the point is, pay attention to the jumps. The jumps will tell you how many electrons is there in the valence shell, and that will tell you the group number. Okay, and then interpret successive ionization energy of an element in terms of the position of the element within the periodic table. Again, this just allows the analysis that I've just covered just now allows you to figure out the period and the group number of that particular element. Okay, so that's all for the content for the chapter on atomic structure, and then I'm just going to cover the questions as checklist for the part on atomic structure to practice the concepts that we have learned just now. Okay, so November 2017 A-level question. The table gives the successive ionization energies for an element X. So the first IE is this, so on and so forth. So again, the most important thing is just to figure out like where is the jump. So notice that, right? Okay, let me see if I can quickly. Is it here? No. Yeah. Pencil. So you see that, notice from here to here, right? This is a value of 850. This is a jump of 900, which is not too much different from 850. Then this is a jump of 2001, which is kind of like quite different, right? And then from here to here is, oh wait, did I get it correct? Yeah, 2001. So this is like 1002. Whereas from the 5th to the 6th, right, it's 6300. Okay, let me see. So 850, 900, 2001. Yeah, no, I understand that this 2001 seems to be larger than this. It's actually like a jump, but the most significant jump is really from the 5th to the 6th ionization energy. So what it means is that the 6th electron that's removed is from the inner principal quantum shell, and hence there's actually only 5 electrons in the valence shell. So first electron from the valence shell, second from the valence shell, third from the valence shell, fourth from the valence shell, fifth from the valence shell. The 6th one is suddenly from the inner principal quantum shell, and hence the amount of energy required to remove the 6th electron is actually much larger than that of the 5th one. Since there's 5 electrons in the valence shell, we will know that the group number of this element is group 5. And what could be the formula of the chloride of X? Since it's in group 5, it will be XCl3. Okay, so I understand that we haven't learned bonding yet, but from your secondary school chemistry, right, if you are in group 5, you are non-metal. And if, okay, so as a concrete example, let's just say phosphorus, which is in group 5, right? You need to form, okay, you have 5 electrons, so your 3 electron set of octet configuration, which is what you need to have when you form bonding, stable octet configuration. So you need to form 3 covalent bonds, and hence the answer will be PCl3, because in PCl3, right, back to the old way of drawing dot and cross diagram, you will have like 1, 2, and then like 1 cross and 1 dot for chlorine. 1, 2. Okay, sorry if it's not very clear. Okay, PCl3. If you were to count the number of electrons around the phosphorus atom, like the 5, 1, 2, 3, 4, the 5 crosses, those are the original, those are the original electrons of the phosphorus, group 5, so 5 valence electrons. And then like if you include the 3 electrons that's being shared by the 3 chlorine atoms, it will have a total number of 8 electrons, which is basically stable octet configuration for the phosphorus. Okay. Yep. Okay. 2007 question. The graph shows the first 13 ionization energies for element X. So immediately, what can we deduce from X from the graph, right? So let's ignore all the options first. So we see that like there's a big jump from the second to the third one, which means that this electron is from the inner principal quantum shell. Since the third electron is from the inner principal quantum shell, this two must be from the valence shell, which must mean that there is exactly 2 electrons in the valence shell, and hence we know that it will be in group 2. Okay, without looking at just to analyze this graph. Okay, then like there's 1, 2, 3, 4, 5, 6, 7, 8. So there's next 8 electrons in the next inner principal quantum shell, and then there seems to be 3, but we cannot conclude here because the question says that the graph shows the first 13 ionization energies for element X. We do not know whether like this is all the electrons there is for element X. If we were to continue, then we cannot conclude that basically there's only 13 electrons. However, based on this jump, like I said, emphasize again and again, the jump is the most important thing because it allows you to figure out the number of valence electrons, which will allow you to figure out the group number of the element, which is kind of the most important thing in chemistry anyway, because like in chemistry, right, only the valence electrons are important. Only the valence electrons take part in chemical reaction. So if you're able to figure out the group number, you'll be able to figure out the number of valence electrons that it has and the way that it will participate in different chemical reactions. Okay, we can't say that whether is it a D block element because we do not know the total number of electrons that it has, but we do know that it's definitely group 2 of the periodic table. It's not in group 3 because it does not have 3 valence electrons, and we do not know whether is it wait, let me see. It's definitely not in the second period because from these 13 ionization energies, right, we will know that it definitely has more than 10 electrons. And if you have 10 electrons, it's impossible for it to be in the second period because if you were to look at the periodic table here, right, the second period only extends up to 10 electrons. So if you have 13 electrons, it's minimally from period 3. It's not necessary that it's in period 3, but there's just absolutely no way that it can be from period 2. Right? So the answer for this is B. Okay, so the first 6 ionization energies of an element M in kilojoules per mole are shown. So M forms its only chloride by heating M with chlorine. So again, the important thing is to figure out the increase in the ionization energy from one to the next, and to decide where is the big jump. So from this to this is like 607. From this to this is what? Let me see, 951. I'm just doing this off my head, right? So hopefully it's right. 951. Then from here to here is like 1000. Around in the order of like 1001. I'm not going to be exactly exact, right? It's not exactly 1001, but that's not important because like we are trying to figure out where's the big jump, right? But notice from this 3003 to 7008, it's like 4005, right? So clearly this is the jump, right? There is a huge jump from the 4th ionization energy to the 5th ionization energy, meaning that this 5th ionization energy must involve the 5th electron must be removed from an inner principal quantum shell, and hence there are exactly 4 valence electrons, which will now tell you the group number of element M, which means that it's in group 4. Okay, it's in group 4. But of course, like, you need to be well versed in your chemical bonding, because like after you decide that the element is in group 4, right, how do you know what is the chloride that it will form when you heat M with chlorine? So group 4, when you react with chlorine, so group 4 is actually a non-metal, which means that, and group 4, it has 4 valence electrons, which means there's 4 electrons short of stable octet configuration. So if it has 4 electrons short of octet configuration, chlorine on the other hand is in group 7, so it's in group 7. So it has 7 valence electrons and it's only 1 short of octet. So in order for M to react with chlorine, 1M needs to share with each electron with 4 different chlorines so that you can get a stable octet configuration. So let me just draw the dot and cross diagram for MCl4, right? So like, okay, I'm just going to simplify it as like that. Cl, then dot, 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 dot. Okay, so like M has 4 valence electrons, the 4 crosses, and it shares 1 electron each with each of the chlorine. So like 1, 2, 3, 4, and if you were to count the number of electrons that it has in the outer shell for M, it will be 1, 2, 3, 4, 5, 6, 7, 8, just nice of stable octet configuration, and hence it will actually form MCl4. So the correct answer will be this, because it actually forms MCl4 just by So what we did was that we figure out, based on this jump in the ionization energy, what group this is in, and we asked if we have a group 4 element, how will it react with chlorine, and what is the final product that will be formed. So the answer will be MCl4, and this will be the answer to the question. Okay, so basically that wraps up for the chapter of atomic structure. Like if you all have any questions, just type it in the comments and I'll be happy to answer them. Okay, so I'm supposed to start on the chapter of chemical bonding, but I guess that we have covered like quite a bit of stuff today. So I guess I will leave the chapter of chemical bonding to the next for y'all to digest it and to think if y'all have any questions to ask. So I'm just going to leave the stream for today, and I'll see y'all next week again. Okay? Yeah, I hope y'all enjoyed the material, and if y'all like the stream, just like and share so that more people can come to know of it and to benefit from this content. Okay, very good night to one and all.